Hello everyone, in this part of our lecture we're going to do another circuit problem again. We are studying how to transform time domain circuits into Laplace domain, S domain, frequency domain, and then we were solving these circuits in S domain as well. And once we find any expression in the S domain, we run this initial and the final value theorems to see whether it makes sense the time domain values and the S domain values are okay. And then we inverse transform the Laplace transform functions to get the time domain functions to solve the final circuit. So in this part of the lecture, we're going to do an RLC circuit and the step response of that, but in the S domain. You have seen this circuit before as well when we were working on chapter number 8. And again, this is a step response of an RLC circuit where at time t is equal to 0, this switch opens up, right? So when this switch opens up at time t is equal to 0, this current source is going to come into play or come into circuit, and then it is going to start to supply energy to the capacitor and inductor. Okay, so this is a step response. You bring in a source at a switching event. Another interesting thing already given in this question is that the initial inductor current is 29 milliamperes and the initial voltage across the capacitor is 50 volts, right? So I know the value of my I naught, which is 29 milliamperes, and the V naught is 50 volts. Okay, so let's get started, right? And I need to find the value of the VT here, right? The voltage across a 500 ohms resistance for T is greater or equals to 0. So again, if you remember, the first step is always finding the initial conditions that are written in the question. I naught is 29 milliamperes, and the V naught over here for the capacitor is 50 volts. So these are the initial conditions given. So great. Step number 2 is we Laplace transform the independent sources. After the switching event, I have an independent source, 24 milliamperes in the circuit, right? So I need to Laplace transform the current source, right? Laplace transform 24 milliampere current source. One more important thing, since this source came into the circuit at t is equal to 0, so we also learned that we can represent by a step function. So essentially this is 24 times u of t, and the Laplace transform of 24 u of t is 24 over s, and again this is milliamperes, right? Milliampere seconds. Okay, so after finding the Laplace transform of this, the third thing that we need to do is we essentially any other voltages and the current variables we Laplace transform as well. So for example, we are interested in finding this voltage V, the Laplace transform of that. So I'm going to create a Laplace transform of this variable, which is going to be just capital V. Okay, great. The fourth step is always finding the S domain circuit. Now we need to start finding the S domain circuit. Okay, so before I find an S domain circuit, I know that I already figured this thing out, the S domain of this current source, which is 24 over S here, right? I know 500 will remain 500, but I do have an inductor and a capacitor. And what to do with an inductor and a capacitor? We have to use one of the models of the inductor and the capacitor. If you remember, we can, if there are initial energies present in the inductor and the capacitor, and they have initial conditions, over here we do have initial capacitor voltage is 50 volts and the initial inductor current is 29 milliamps. We have to pick either one of them, a series model or a parallel model of an inductor and a capacitor in the S domain. Which model makes sense over here? Since everything is connected in parallel, so maybe picking just a parallel model makes sense, right? And you're going to see that why it makes sense as well, because it is going to be much more easier to solve, right? Since all components are connected in parallel, picking a parallel S domain model for inductor and capacitor is more suitable. By the way, you can pick any one of them and you should be able to solve the circuits if you know how to solve a circuit, right? But just to make the life easier, or maybe just reduce a couple of steps more, it's much more easier to pick the right model. If you were to pick the other model as well, that is the right model too, right? I'm going to pick up parallel model because everything is connected in parallel, and this would be easier to solve a circuit. If I were to pick a other model, which is a series model, I would still be able to get exactly the same answers. I just have to solve like another couple of steps, right? Okay, anyhow, now I need to model this thing, right? A capacitor and an inductor. So let us start with, if you remember, right, the model of an inductor was, the parallel model of an inductor was, you had an inductor, right? And you had a current source. This was your current I. This was your SL. This was your V. And this was your I naught over S. Okay? And this is how the current is going. Okay. So for example, what is SL? SL is your impedance, ZL, S times L. So the SL should come out to be, what is SL? 25 millihenry times S. So the impedance should come out to be 0.025S, or ZL is S over 40 ohms, right? You already know the value of I naught. I naught is 29 milliamperes. Okay, so I can replace this thing, this inductor, with these two branches now. I'm going to do that in a second, because let me do the capacitor as well, and then I'm going to replace this. But I have to create two parallel branches rather than this inductor. One branch is going to have this inductor showing as an impedance SL, and the other branch is going to have a current source I naught over S, which is 29 milliamperes divided by S. Okay, so let's do the capacitor as well. Okay, the model of a capacitor is, you got this, you got a capacitor here, and you got another current source, right? Okay, this is also I, and over 1 over SC, which practically represents the capacitance impedance, V and CV naught, and this. Okay, now again, you are gonna have ZC, which is 1 over SC. What is 25 nanofarad, right? 1 over S. 25 nanofarad is 40 times 10 to the 6. ZC is 40 times 10 to the 6 divided by S. Okay, and this again, V naught is coming from here, 50 volts. So I'm going to replace this capacitor now with this model, where I know the value of SC, the ZC over here, right, which is 40 times 10 to the 6. And in the other branch, I'm going to connect as a current source of CV naught, right, or the capacitance is C, which is 25 nanofarad times V naught. Right, basically I can do CV naught over here as well, which is 25 times 10 to the minus 9 times 50. So the capacitance, CV naught, comes out to be approximately 1.25 microamperes second. Similarly, let me do this I naught over S. I naught over S will remain I naught over S, because you already have an I naught, right? Or you can, if you want to write I naught over S, should be 29 milliampere seconds. Okay, so I'm going to convert this into in a second. Okay, so now we are going to make the equivalent circuit model over here. The resistances, the 500 ohms will remain as is. 24 milliamperes will become 24 over S. Milliampere second, a capacitor will convert it into these two branches, inductor will get converted into these two branches, right? Okay, so I'm going to draw a S domain equivalent circuit. S domain circuit now, right? So first you have this 24 milliampere source, which got converted into 24 over S, right? And let's write the units as well, milliamperes times seconds. Then I'm going to model a capacitor. So the capacitor has this, sorry, what's, there was something happening, let me redo it. Okay, so the capacitor has the ZC, which is 40 times 10 to the 6 over S, and the other branch CV naught, which is 1.25 microamperes per second. Okay, so this was 40 times 10 to the 6 over S. Again, this was in ohms, and a current source attached to it, which is again CV naught, and that was equals to 1.25 micro amperes second. Then I'm going to model an inductor with first initially with an impedance, which came out to be S over 40 ohms, if you remember. And then it can be modeled with another current source over here, which was I naught over S, so 29 milliamperes second over S, which is 29 milliamperes second over S. And then finally I'm going to have a resistor, and here's a voltage across a resistor, and this is 500 ohms. Okay, now this looks a pretty good circuit and a simple circuit now, as I can see that this circuit has practically 3 current sources. This one is a second one, this one is a third one, and it has 1 resistance and 2 impedances. So essentially what I have to do is I have to find the equivalent current and the equivalent resistance and simply find the voltage V. Okay, so let's do that. Okay, so the next step number 5, I need to find V naught over S. Oh, sorry, this V over S. In order to find V over S, I am going to solve first. I'm going to find the equivalent impedance, right? Equivalent impedance is again, let me do 1 over 500 plus what is the inverse of 29 milliamps second over S over 4000. 29, this was the current, right? So S over 40, 1 over S over 40 is 40 over S, plus 40 times 10 to the 6 over S should be S over 40 times 10 to the 6. Yes, okay, great. And of course this should be the inverse of it, because we are taking Z equivalent, or 1 over Z equivalent should be the term in the bracket. Okay, so if you were to solve the Z equivalent, you're gonna get, or the answer that you're gonna get is 40 times 10 to the 6 S divided by S square plus 80,000 plus 16 times 10 to the 8 ohms. Okay, so this is the Z equivalent that you got, right? Now what I need to do is to find the overall current. So for example, again, this final V of S should be equals to I times R. I'm going to call it Z equivalent times I equivalent, and I have to find I equivalent, right? Let me call this Z equivalent as is. In order to find I equivalent, I know that I have 3 current sources. This, you can consider any of the nodes. Let's say this is a node L, right? At node L, I can see that 24 by S milliamps second is going up, 1.25 microamps second is going up as well, and this current source 29 over S milliamps second is going down, right? So I have 2 currents going up, 1 is going down, so I can easily write a Kirchhoff's current law, right? So I'm gonna write Kirchhoff's current law over here in I equivalent to find I equivalent. So I equivalent is starting with 24 over S, 24 milli over S. Why don't I simplify it? 0.024 over S plus the other current source is 1.25 micro, right? Which is 1.25 is 10 to the minus 6 minus the third one is going down, right? So 29 milli, 0.029 over s. 0.029 over s. Okay, so if you were to solve this and multiply with z equivalent, which we computed over here, you're gonna get the value of the v of s. So v of s should come out to be 50s minus 20 times 10 to the 4 divided by s squared plus 80,000 plus 16 times 10 to the 8. And again, this is volts second. Okay, great. So I ended up finding my voltage value with respect to S. Now I have to apply step number 6, where I apply initial and the final value theorem. Something is of my marker. Apply initial and final value theorems, right? And we do this as a kind of a sanity check, if you remember, right? So I'm going to start with applying the initial value theorem. Initial value theorem states that the initial value of the time domain should be equivalent to limit s approaches to infinity s of v in the frequency domain, right? So again, limit s approaches to infinity s times 50s minus 20 times 10 to the 4 divided by s squared plus 80,000 plus 16 times 10 to the 8. Okay. Again, I'm going to do exactly the same thing. I'm going to divide the numerator and denominator by s squared to create this 1 over s term, right? Let me call it divide numerator and denominator by s squared. So if I'm going to do that, I will get limit 1 over s approaches to 0 equals 50 minus 20 times 10 to the 4. Again, this term would become 50s squared minus 20 into 10 to the 4s, right? So if you're going to divide by 50, this by s squared, 50 minus 10 to the 4 times 1 over s. Times 1 over s divided by, in the numerator I'm going to divide s squared will be divided by s squared, 1 plus 80,000 1 over s square. No, so it should be 80,000. Where is the equation? Okay, so the final V actually came out to be, sorry, I forgot. This came out to be 80,000 s. And this is coming all the way from here. That I forgot to put in. 80,000 s. And that is why this should be 1 over s. Okay. Plus 16 times 10 to the 8, 1 over s squared. So if once you're going to apply the limit, 1 over s equals to 0. So you're going to get 50 divided by 1 plus 0 plus 0. So your answer is going to come out to be 50. Interesting. Now let's see whether it makes sense or not in the time domain, right? So it says that in the time domain, your voltage over here at t is equal to 0 positive should be 50 volts, right? So essentially what this thing is saying is that V naught, which is, sorry, let's call it this V, voltage across the resistor V, at 0 positive should be 50 volts. Okay, and I want to kind of prove it, right? So I'm going to come over here, look at the circuit at t is equal to 0 positive just after the switching event. I know that my capacitor was open circuit, which has an initial value of 50 volts. So if the capacitor has an initial value of 50 volts at t is equal to 0 positive, since the capacitor voltage cannot change instantaneously, so the voltage across this resistor is going to be 50 volts as well. So this makes sense. Initial value theorem, everything checks out. Now let's apply the final value theorem as well. Apply final value theorem. And again, final value theorem states that the final value in the time domain at time equals to infinity can be computed by doing the things in the S domain by essentially following this function. Limit s approaches to infinity, s of v of s. Okay, so again, let me apply this limit. S approaches to 0, and again, here was my function. This was my function. No, okay, this was my function, which is 50s square, 50s square minus 20 times 10 to the 4s divided by s squared plus 80,000 s plus 16 times 10 to the 8, right? And if I'm going to apply this thing to 0, I'm going to get 0 over 16 times 10 to the 8, which should come out to be 0. So this means that, and again, this is t approaches to infinity, f of t, which is v of t. So let's see now whether what is the v at t equals to infinity over here, right? So what is the, here's the time domain circle, right? So what is this voltage at infinity? At infinity, this voltage should be 0 because once a new steady state will be reached after the switching event, that will short circuit the current, right? It should be 0 because inductor will behave as a short circuit. Okay, perfect. Sounds good. So the final thing now is I have to find the v of t from v of s. I already know my v of s, which was again, where's the value? 50s minus 10, sorry, 20 times 10 to the 4. 20 times 10 to the 4 divided by s squared plus 80,000 plus 16 times 10 to the 8. Okay, so this was my voltage v of s, and I need to practically like Laplace transform of v of s, inverse Laplace, and find v of t. So this is what I need to do. I can easily see that I've solved this kind of functions like so many times in the past chapter. I need to, this is a proper rational fraction where the power of the s in the denominator is higher than the numerator. I think in the past part of the lecture I mistakenly said that was an improper rational fraction that I mistakenly said it to be proper. However, right, so in the proper rational fraction, your denominator s power should be higher than the numerator s power, higher s power. We have solved this fractions like innumerable number of times, so I'm not going to do it. I'm just going to show you the expansion and then I'm going to write the results, right? So for example, this v of s, which is 50s minus 20 10 times 4 over s squared plus 80,000 plus 16 10 to the 8 can be rewritten as 50s minus 10 to the 4 s plus 40,000 square. This is the repeated real roots, and we also learned how to solve for the repeated real roots, right? Where 50s minus 20 10 to the 4 divided by s plus 40,000 square can be written as a over s plus 40,000 plus b over s plus 40,000 square. And then again, use the techniques that you have used in the past to solve for both of them and find the coefficients a and b. And once you're going to find the coefficients, the v of s should come out to be minus 2.2 10 to the 6 over s plus 40,000 square plus 50 over s plus 40,000, right? So essentially your A coefficient comes out to be 50 and B is minus 2.2 into 10 to the 6. Uh, yeah. Okay, so once you do that, now you have to find the inverse Laplace transform. And I also know that from the past, the Laplace transform of k over s plus a is, sorry, the inverse Laplace is k times e raised to the power minus 80 u of t. And I also know that k over s plus a whole square inverse Laplace is k times t e raised to the power minus 80 u of t. So I'm going to use both of these identities to write the final version. So time domain v of t should come out to be k minus 2.2 into 10 to the 6, right? E raised to the power minus 40,000 times t plus constant 50 e raised to the power minus 40,000 u of t. Okay, so this is your time domain function v of t across that resistance, 500 ohms. Okay, so this is how you can kind of solve these circuits. Again, in terms of summary, this was an interesting problem where we had this parallel RLC circuit, and a step response where our inductor, where our current source comes into play after the switching event and start to supply the energy to the inductor and capacitor. Again, in order to solve any, I'm going to do a few more examples in the next lecture, but in order to solve any of these circuits, again, you start with finding the initial conditions, which were given in this question, 29 and 50 milliamperes. Then you Laplace transform the independent sources, right? So the Laplace transform of this source, 24 milliamperes. First, since this was after the switching event, so we multiplied the step function. Then we take a inverse Laplace transform of 24 milliamps multiplied by the step function, and that came out to be 24 over s. Then we found the Laplace transform variable for this v, which is just essentially just going to be capital V. And then we to make the equivalent circuit models of an inductor and a capacitor. Since everything was connected in parallel, so I ended up picking the parallel models of the S domain, capacitor, and inductor. Once I solve for this, this parallel beautiful circuit becomes very simple because I just have a resistance and the two impedances, ZC and ZL, connected in parallel, and I have three current sources all in parallel. So I found an equivalent resistance, equivalent impedance, and I also found an equivalent current by applying a Kirchhoff's current law. So my V of S can be easily computed. So once I found my V of S, I applied the initial and the final value theorems. And we also cross-checked after applying the initial value theorem, which is finding the initial value of the of a particular variable, in this case V of t, across the resistor. So we applied the initial value theorem in the frequency domain, the S domain, and found the value to be 50 volts. And then we saw that if we looked at a circuit in the time domain, it actually is 50 volts. And then we also applied the final value theorem, which came out to, and the answer came out to be 0. Then we looked at the circuit and saw that in the time domain, if we were to look at that voltage value at infinity, it is going to be 0. So that makes sense, and both of the values match. Then we had to take an inverse Laplace transform of the function v of s. So we first we have to factorize it and convert this into partial fractions, and then we ended up easily taking an inverse Laplace of this function v of s here to get the final value of the function v of t. So this should end this lecture. In the next lecture, we're going to do a few other example problems, and we're going to move on the next topics. All right, sounds good. Thank you so much. Have a great rest of the day. Thanks. Bye.